Welcome to our video on basics of complex numbers. We have been using complex numbers throughout the course, so hopefully some of this notation and vocabulary will be familiar to you, but I want to be sure we're all on the same page before taking our deep dive into complex analysis. So of course, a complex number is an expression or a symbol of the form x plus I times y, where x and y are real numbers, and the symbol I satisfies I squared equals minus 1. We will very often identify the complex numbers c with ordered pairs of real numbers in R2 via the identification that sends x plus iy to the ordered pair x, y. And I will sometimes draw graphs in C in the complex plane with our x-axis labeled as the reals and the y-axis labeled as I times r, the purely imaginary axis. So here's the sort of axes I'll be giving you frequently. Horizontal axis is real, vertical axis is purely imaginary, I times r. So if we take a complex number z equals x plus iy, then we have a lot of notations to review. So the real part of z is of course x. The imaginary part of z is of course y. The modulus of z is the square root of x squared plus y squared, sort of the length of z. The conjugate of z is z bar equals x minus iy. And it's a quick calculation to show that the modulus of z squared equals z times z bar, as we know already. And one of the most useful things we can do with complex numbers is write them not necessarily as x plus iy or as ordered pairs xy, but in polar coordinates. So let's say we're in R2, purely real land, not complex land. If you have an ordered pair xy in R2, and at least one of the coordinates x or y is non-zero, let's define r to be square root of x squared plus y squared. So r is basically the modulus. And then calculus reminds us that we can find theta in the reals such that we have x equal to r cosine of theta and y equal to r sine of theta. And of course we have infinitely many such theta because cosine and sine are 2 pi periodic. So I've gone from having an ordered pair xy in R2 to representing x and y with these sort of shared coordinates r and theta, the polar coordinates. So if I take a non-zero complex number z, I should be able to write the real part of z is r cosine of theta, and the imaginary part of z is r sine of theta, where r is going to be the square root of the real part squared plus the imaginary part squared, which is of course the modulus of z. And so z, which is of course equal to the real part of z plus I times the imaginary part of z, is now equal to r cosine of theta plus I times r sine of theta. And I factor out the r, that's r times the sum cosine of theta plus I sine of theta. Or that's the modulus of z times the sum cosine of theta plus I sine of theta. So this is how polar coordinates look in the complex plane. Let's say we take z equal to 1 plus I. How can we write this in polar coordinates? Well, first we'll recognize 1 plus I, the complex number, as basically the same as the ordered pair 1, 1 in R2. So we compute the modulus of this complex number. Modulus of 1 plus I is square root of 1 squared plus 1 squared, which is square root of 2. And then we think about that angle theta. Trigonometry tells us that the line segment going from the origin 0, 0 to the point 1, 1 makes an angle of pi over 4 with the positive x-axis. And so we get 1 plus I should be square root of 2 times the sum cosine of pi over 4 plus I sine pi over 4. And of course you could check out the trig with cosine pi over 4 and sine pi over 4 and turn that back into 1 plus I. So here's a new vocabulary word. If we have a non-zero complex number z, an argument of z is any real number theta such that we have the representation z equals the modulus of z times the sum cosine of theta plus I sine of theta. So the argument of z is just the angle for z from polar coordinates. But we don't just have one argument, right? Because if I have one argument theta here, I could replace that with theta plus 2 pi, or theta plus 4 pi, or theta minus 60 pi, any integer multiple of 2 pi. So really I have a set of arguments, a set of numbers that satisfy this relation z equals modulus of z times the sum cosine of theta plus I sine theta. And we will call the set of all arguments of z arg of z. And importantly, I'm writing this lowercase arg of z. So the challenge is that if you have an argument theta 0, then theta 0 plus 2 pi k is an argument for any integer k, thanks to the 2 pi periodicity of sine and cosine. So there's a bit of ambiguity, right? If I'm talking about an argument of z, well, I haven't really specified which one. I have to consider everything in the set of all arguments. And often we don't write the set of all arguments in curly braces in set theoretic notation. Often I'll just write something like arg z equals theta 0 plus 2 pi k, where theta 0 is one particular argument. So I'll just eliminate the braces, and when you see that k there, you should interpret that meaning all integers k. So for example, above in that example 3.1.1, we found that one argument of 1 plus I was pi over 4, so arg of 1 plus I is pi over 4 plus 2 pi k, where I'm interpreting this as all integers k. This is a bit ambiguous, and while polar coordinates, as we'll see, can be very useful for representing complex numbers and doing arithmetic with complex numbers, we have to balance the utility of polar coordinates with the ambiguity of the argument, and that's going to come up time and again in different calculations and definitions. So it's worthwhile specifying one special argument, and we will call the principal argument of a non-zero complex number to be the unique number in the interval open at minus pi, closed to pi, the unique number in that interval such that z equals modulus of z times the sum cosine theta plus I sine theta. So the power of the principal argument is that I'm telling you where this particular number lives. It has to be bigger than minus pi and less than or equal to positive pi. And we will use the notation capital A arg for this principal argument, sort of if you're a pirate, arg of z, and pronounce it a little more evocatively. One caution, different books, different papers sometimes take the principal argument to be in slightly different intervals, maybe closed at minus pi, open at positive pi. It doesn't exactly matter as long as you are consistent, and this is the decision we're going to use for principal argument in our remaining weeks together. And importantly, capital arg of z is a single real number, whereas lowercase arg of z is a set of real numbers. And we will come back to this tension between single real numbers and set of real numbers again and again in our calculations.